Okay, so we're going to break up section 1.4 up into two parts because it's quite heavy. So on this episode of the Learning Channel, we are going to kind of introduce this concept of the velocity problem. But before we could do that, we're going to have to define a couple of things. So let's take a look here. And here we need to understand this word tangent. And I like how this is very similar to functions, how it is derived from the Latin word tangens. However, that means touching. So when you think of a tangent, you think of a line touching a curve. But that line must touch a curve at a single point. At a single point. And that tangent line must fall in the same direction. So we're going to get into how can this idea become precise. We're getting to that. But keep in mind that when you're dealing with the word tangent, it's tangent line to a curve that is going to touch the curve at a single point. And again, the tangent line intersects the graph of a function at a single point. And why are we so interested with this tangent line? Why is this tangent line so popular? Well, the tangent line is going to indicate that we could find the slope of that tangent line, and the slope represents a rate of change. So we're going to be looking at the rate of change at a single point on a particular curve. And you see here, once we calculate this slope, is the slope going to be positive or negative? Positive because it's rising. Is this slope going to be positive or negative? Negative because it's falling. And in this particular case, again, the slope of the tangent line is going to represent that rate of change at that position. The position is a point. So there's kind of quite a few ways to interpret this slope of the tangent line, but it's really, really important that we get these key concepts down. So now that we talked about what a tangent line is, and we talked about what it represents, now in this particular case, the key question is, well, how are we going to find that slope of a tangent line? Well, let's think about this, right? If we set the slope, and the slope here is going to be the tangent line, in this particular case, wasn't it y2 minus y1 all over x sub 2 minus x sub 1? And here you need 2 points. But isn't the slope of the tangent line intersecting at a single point? And so in that particular case, at that single point here, 1 minus 1, well, if that was my point, let me just illustrate, if my point here was 1, 3, and these x's are the same, then the denominator is going to give you 0, and you cannot have 0 what? In the denominator. So in order for us to find the slope of the tangent line, we are going to need to use the slope of a secant line. And so let's take a look here. So in this particular case, secant line comes from the Latin word secans, meaning cutting. So tangent line was more touching, secant line is more cutting, and it's going to cut the graph at more than one point. And so you could think here, the secant line intersects the graph of a function at 2 particular points. So let's take our basic friend here, which is the quadratic curve. And let's take this point here, P, at point 1, 1, which represents, sorry, I misspoke. P is this pink tangent line at point 1, 1, and Q represents, to point P, represents the secant line. So what this is going to illustrate, how do we find the slope of a secant line between 2 points P and Q? How do we find the slope of the tangent line at point P? That is the question, right? And so in this particular case, and don't worry about writing all of this down because it is in the textbook. I'm just kind of giving a voiceover of it. But in this particular case, if you wanted to find the slope here, and let's say you called this point 2, and this one here point 1, isn't this going to be the change in y, which is x squared minus 1, which is going to be all over x minus 1. So now you have the slope of the secant line represented in terms of x. So what this is going to illustrate that we could use specific values for x, any value, but we can't use 1. So if you pick a value here, let's just say 1.5, well, if you square 1.5, what is 1.5 squared? Is that 2.25? I think it is, yeah. So that would be 2.25. So if you find that slope, you're going to get m to be 2.25 minus 1, which is going to be all over 1.5 minus 1. And when you do this calculation, using your calculator, then what that is going to give you, do that over here, is going to give you 2.25. So the slope of that secant line at the point Q being 1.5 and 2.5 and P being at 1, 1 will be 2.5. However, the goal here is to take points that are going to get closer and closer and closer to P, and this here would be considered the right. And then on this side, take points closer and closer and closer and closer to P, which would be considered on the left side, and see where those slopes are approaching, right? Approaching. And that's a lot of work, right? So your text did the legwork for us that now if we use the slope of the secant lines by picking points getting closer to the tangent line, notice what's happening with these slopes. So on this side, right, these are the values that are coming in from the right that are getting closer and closer to 1. And notice that the slope is approaching 2. And these values of x are coming in from the left, and these slopes are approaching 2. So using the slopes of the tangent line, we're able to say that the slope, I misspoke. I wanted to say using the slopes of the secant line, we could say that those slopes of the secant line are approaching the slope of the tangent line, which is going to equal 2. And this represents the rate of change at this particular point. And this rate of change is an increase, and if it was negative, then it would be a decrease. So you can see there's quite a bit of work here, right, to find the slope of the tangent line. But it's a major concept that's going to get into the velocity question in a few minutes. And so basically, this is just an illustration that this was your first initial 2 points, this is your second 2, this is your third 2, and you see how it's getting closer. So when the blue line appears to be on top of the pink line, then the secant line is approaching that tangent line, but from the right. And again, if you take 2 points here, 2 points here, 2 points here, then those points are coming from the left. But now we have fancy notation. That word approaching is going to use this concept of a limit. So the limit, and look at how this notation here, Q is approaching point P, and this is the slope of that secant line is going to equal m, which is the slope of the tangent line. And so the slope of the tangent line is the limit of slopes of the secant line. This is something that you want to drill. This is the concept component. This here is the notation component, right? Notation is another way of saying the formula. And then again, the limit as x is approaching 1, now we have our slope in terms of x that equals 2 by using this table of values. Then the next question up to play is we could now find the equation of a tangent line at that point. And so again, you need to know the formula for point slope. Once you have that, y minus 1 will equal 2 times x minus 1. Distribute y minus 1 equals 2x minus 2. Hence, y equals 2x minus 1, which would represent that equation of the tangent line. And now we're going to take a look here at a problem that is going to use this particular table.